So folks, we've come to the end of this. Now that we've got our two principles of superposition, we're basically ready to give our full theory of solving nth order linear differential equations. We still have plenty of kinks to iron out, and we'll learn some techniques, but the theory is just about complete. So, in this case, I'm given three solutions, phi1, phi2, and phi3, and I'm told that they all three solve this differential equation here. Well, this differential equation has a couple of special properties that we need to highlight. Okay? The ODE here is linear and homogeneous. What that tells us is that the first principle of superposition applies. What do I mean by that? Well, the first principle of superposition says if you've got two or more solutions to and let's be very careful here, to a linear homogeneous ODE, then any linear combination of those two solutions is also a solution. So here I ask, what else is a solution? Any function of the form y sub t equals c1 x squared plus c2 x squared natural log of x plus c3 times 1 over x. Any function of this form solves this differential equation, and we don't need to check it anymore because the principle of superposition verifies that for us. All we need to confirm is that the ODE is linear and homogeneous, and so we can write any collection of solutions, well, any linear combination of that collection is again a solution. Now, look at the next question and see how it's different than what we have above. Do a double check here, folks. What do you notice about this ODE? This ODE has some special properties, but not quite as many as the previous one. This ODE is a linear ODE. Now, it's not linear homogeneous, so I can't say necessarily that any linear combination of this solution is again a solution. For example, we don't know if c times 1/4 x to the third solves the ODE. We don't get the fact that some multiple of a solution is again a solution the same way we did for linear but homogeneous, because this is not necessarily homogeneous. It's non-homogeneous. But still, we know that this corresponding homogeneous ODE looks like this. So we're going to start saying this a few times, folks. The corresponding homogeneous ODE would be what? It would be x cubed y triple prime minus 2xy prime plus 4y equals 0. That's the corresponding homogeneous ODE. Has solutions, phi1, phi2, phi3 as above. So we know this function right here, y sub t equals c1 x squared plus c2 x squared natural log of x plus c3 times 1 over x plus this solution, this one particular solution, 1/4 x to the fourth, solves x cubed y triple prime minus 2xy prime plus 4y equals x cubed. How come? Because of the linearity of the left-hand side, that linear transformation, this component right here will all, because of linearity, this will all get mapped to 0, and then this solves the non-homogeneous ODE, and so their sum will also solve the non-homogeneous ODE. Okay. So here we go. This is our overview of the theory of solving nth order linear differential equations. First of all, we solved the corresponding homogeneous equation to find YH. By YH, I mean a general or the general solution to the linear differential operator L sub y equals 0. Then we need to find a particular solution, i.e. some y sub p, so we take L y sub p, we get out f of t. And this is where I'm saying that our differential equation has this f of t forcing function. Then we can express the solution. This is our general solution to the nth order linear equation. It would be our homogeneous general solution plus the one particular solution. By the way, our work today, we should say, is enough to verify that solutions to a given nth order linear, this is homogeneous, ODE forms a vector space. I want you to confirm that by reviewing your definition of what we mean by a vector subspace, and then look at statement number 11 in this handout. So we'll do one critical example now in the next video where we put all this together a little bit more concretely.